Hello and welcome to our lesson on the law of sines. So the law of sines is going to allow us to find missing sides and or missing angles of triangles that aren't necessarily right triangles. So all of the work that we've been doing thus far has been with right triangles. The triangles that we used to build the unit circle were right triangles. We had 30, 60, 90 and 45, 45, 90 triangles, and then using sine, cosine, tangent, using Pythagorean theorem, all those rules applied to right triangles, meaning all of those triangles had a right angle. So triangles containing a right angle we know are called right triangles. Now I want to go through a little bit of background on some other types of triangles before I show you how we can use what we call the law of sines to also find missing sides and angles. So if a triangle has a right angle, we call it a right triangle. If a triangle does not contain a right angle, it's called an oblique triangle. It's possible that you've never heard that term before because oblique triangles break into two categories that I'm sure we've heard before. An oblique triangle, it may be what we call an acute triangle. If it's acute, that means it contains all acute angles, or it could be an obtuse triangle, and if it's an obtuse triangle, then it contains one obtuse angle. And just so we're clear, acute angles would be between 0 and 90 degrees, and then obtuse angles would be from 90 to 180 degrees. Okay, not including 90 or 180, because 180 is a straight angle, 90 is a right angle. And then 0 is also a straight angle. So between 0 and 90 is acute, between 90 and 180 is going to be obtuse. So if we have one obtuse angle, then our oblique triangle is an obtuse triangle. And if we have three acute angles, three angles between 0 and 90, then our oblique triangle is an acute triangle. Okay? So there's some terminology. Now, hopefully we also remember that the three angles in a triangle will always add up to 180 degrees total. And there are certain properties that I'll say guarantee unique triangles. So what I mean is, if I was to specify three side lengths for a triangle, there is only one triangle that could be made with those three side lengths. I couldn't rearrange them and make a different triangle. So if we had a side length and a side length and a side length, right? If I gave you three set side lengths, and it's hard to maybe envision this here, but if I gave you three side lengths, gave another student three side lengths, and I said, like, maybe I cut them out, strips of paper. I said, make a triangle out of this. Every one of our triangles would be exactly the same because those side lengths would all be the same. Now, if we specify two angles and a side length that is not between them, we are also going to be constructing the same triangle. So two angles and a side length that's not between them. And by the way, specifying three side lengths, we can refer to that as side, side, side. Or specifying two angles and a side length not between them, we can call that angle, angle, side. So it's an angle, then another angle, and then a side that's not between them. So let's say we had I'm going to draw this as a dotted line. So let's say we had a 40-degree angle, and then we had a 60-degree angle here, and then I told you that this side length was, I don't know, 10. Okay? If this angle created by, we don't know this side length here, but if this angle was 40 degrees and this angle was 60 degrees and this side length was 10, there's only one way to complete the triangle. So we would, again, all be creating the same triangle. And there are proofs for this. I just don't want to get too far into it. But again, certain characteristics that guarantee, if I gave you these things, we would all construct the same triangle. If we specified two angles and the included side, so if I had an angle and then a side and then an angle, what am I trying to draw here? So let's say I had a 40-degree angle here and a 40-degree angle here, and I had a side length here. Again, we're guaranteed, because this angle is going to be stuck and this angle is going to be stuck, we would be guaranteed to make the same picture. And then side, angle, side is, and this is what I was trying to draw a second ago. If I had a side and then an angle and then a side, so let's say I had a 40-degree angle here, this side length was 10, this side length was 10, there'd only be one way to finish that triangle. So these are all different properties that, again, guarantee specific, unique triangles. So we call these things side, 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 angle, angle, side, angle, and side, angle, side. Now there's one in here that's not on the list because it does not guarantee a triangle. We're going to talk about it in a little bit, but it creates issues for us. We'll see it in a minute. So I don't want to spoil anything too quickly here. So we're looking at certain features of our triangle being given to us, but we're going to be asked to solve a triangle. So if we're solving a triangle, that means we're going to be finding all of its characteristics. So solving a triangle means finding all 6 of its fundamental properties, finding all 3 of the side lengths, finding all 3 of the angles. And depending on what information we're given, this could be pretty straightforward, or it may not be, or it may not even be possible. Okay, so before we get into it, here is what we call the law of sines. This is a property that allows us to solve triangles. It's basically telling us that if I wrote a ratio of the sine of an angle and the side that is opposite of that angle, that no matter which pair of angles and sides I choose to write this ratio for, those would all be proportional. So the ratios of the sines of each angle to their opposite sides are all proportional. That means all of the fractions would be equal. So sine of A over A, what I'm looking at is the angle and the side that is opposite of that angle. So if I wrote a fraction of the sine of that angle over its opposite side, or vice versa, put the side over the sine of the angle, either direction this will work, that's going to be equal to any other proportion written in the same way. So for B, here's our angle B. This is the side that is opposite to it. So if I wrote a fraction of the sine of angle B over B, it's going to be equal to the first fraction, which was the sine of A over A. And let me go ahead and not mess up my color coding here. And then the same for C. Okay, so here's angle C, and this is the side that is opposite of angle C. All of those ratios of the sines of each angle to their opposite sides, all of those ratios are equal. And again, this will work in both directions, so I could have angle over side or side over angle, but they're all equal. Now, we won't be using all 3 at the same time. In general, we'll be using 2 fractions at a time so that we have a proportion, and a proportion we can solve by cross multiplying. So if we just have one missing feature in that proportion, then we'll be able to solve with cross multiplication. So for example, here's a pretty straightforward application of the law of sines. If I asked you to solve this triangle, right now we know 3 of its properties. We know 2 of the angles, we know 1 of the sides. Now, knowing 2 of the angles guarantees the 3rd angle, because the angles in a triangle make 180 degrees. So if I have 180 degrees total and I take away the 38 and the 121 that's already in there, that means our 3rd angle, what is this, 159? Our 3rd angle has to be 21 degrees. So there's got to be a 21 degree angle here. So that's pretty easy. Now we know all 3 angles. Now we want to find the remaining sides. So this isn't labeled. I'm going to go ahead and label. It doesn't matter what you choose, but just so that we can organize our work later, I'm going to call these angles A, B, and C, which means this would be side A, this would be side B, and this would be side C. So if I wrote a fraction of the sine of any angle and its opposite side, right, all of these fractions will be equal. Now, when I write my first one, or one of the ones that I'm going to use to solve for something that's missing, and I'm going to actually take the label off of A because it's not missing, we already know it there. I want to use a complete fraction. So, for instance, I know the angle that's here and I know the side that's here. So I can use a fraction of the sine of 38 degrees over the side length of 20. And that's going to equal, now I can put in something that I don't know. So let me use, let's see, how about this one? 121 degrees. So the sine of 121 degrees and I should be putting degree symbols there, over the unknown side, which is C. So if I put that there, that's the only variable in that equation. I can cross multiply to figure out the length for side C, or what I'm calling side C. So if I cross multiply this, then I have 20 times the sine of 121 equal to C times the sine of 38. So if I want to solve for C and it's being multiplied by the sine of 38, I just divide that over. So C is going to equal 20 times the sine of 121 degrees over the sine of 38 degrees. And that is something that we can approximate using a calculator. And just make sure if you're using Desmos or your calculator that you are in degree mode, because the default for just about any calculator is going to be radians. So we have a fraction on the top, 20 times the sine of 121, and then on the bottom, the sine of 38, and that gives us a side length that is approximately 27.85. I think hundredths place would be suitable there. So this side now I can say is not equal to, but is about 27.85. Okay, so there was one. Now I only have one piece left. I know all three angles. I was given one of the sides. I found one of the sides. Now I'm going to find another. And again, I want to use a fraction that I know. And just in case I screwed up with C, I probably wouldn't use that. I would go back to the sine of 38 over 20, because that's one that was given to me. So sine of 38 over 20 is one of my ratios. Now I'm going to write a third here. Here's my angle, 21 degrees. That's going to correspond with this missing side length of B. So I'm going to say that this has to be proportional to the sine of 21 degrees divided by that length B that we're missing. So again, I can cross multiply. Do this one in pink this time. So 20 times the sine of 21 has to equal 21 degrees, has to equal B times the sine of 38 degrees. So again, if I want to solve for B and it's being multiplied by the sine of 38, I will divide that over. So 20 times the sine of 21 degrees divided by the sine of 38 degrees is going to equal B. And then again, we will use our calculator to approximate. And I'm going to cheat. That just needs to change from a 121 to a 21, so B is going to be about 11.64. And there you have it. So this is about 11.64. Our triangle is solved. Okay, we've got all three side lengths, all three angles. Boom. No big deal. Again, a pretty straightforward application of our law of sines. Just writing proportions. The sine of an angle over its opposite side. All of those fractions, all of those ratios are proportional. They have to be equal. Okay? So there's one. Let's look at the next case. We call this the angle side case, by the way, because what we were given, angle side case. No, I said orange. We call this the angle side case because what we were given was an angle, and then a side that was not included, means not between. The side was not between those two angles, so it's literally an angle, and then after those two angles, a side. Okay. So now we're going to look at. Come on, paper. There we go. We're going to look at what we call the angle side angle case. So the angle side angle case will again be a pretty straightforward application. That means we have an angle, then we have a side length here of 11 right in between. It's called the included side. It's in between those two angles. So in this case, we're going to do basically the same thing that we just did. We already know two of the angles, which guarantees us our third angle. 180 degrees total in a triangle. If I take out the 82 and 24, that's already in there. That's what, 106? So that means left over, I have a 74 degree angle. So I know 74 is going to go in there. And I'm going to just call this A, I'm going to call this B, I'm going to call this C. So I have angle A and I have the side that is opposite of angle A. So I have this is my known, okay, this angle, this side. So I'm going to be using that basically twice. So that one is going to help me to find, let's say, I have angle C, but I do not know the side that is across from it. So I'm going to call this little c here. Okay, let me see. Let me write some fractions. So I know that the sine of 74 degrees over 11 has to be proportional to the sine of 24 degrees over c. And now I can solve for c. Cross multiply. So 11 times the sine of 24 degrees has to equal c times the sine of 74 degrees. So I'm going to have to divide that over to get c by itself. So 11 times the sine of 24 degrees divided by the sine of 74 degrees is the exact value for c, and we will approximate that at, let me cheat again here, it's 11 times the sine of 24 divided by the sine of 74, and that's still in degree mode. Okay, just making sure. 4.65-ish, approximately 4.65. So now I can say here, this is about 4.65, and then I just do that again. Okay, again, I'm going to use the given. We had 74 degrees, opposite of that we had 11. So I'm going to use that fraction. And now to find my last pair here, let's see, I know I have an 82 degree angle, but I do not know the length of the side that is opposite of that. And since I called that angle B, I'm going to call this side B. So it's going to be 82 and B I'm looking for. So this is going to be equal to the sine of 82 degrees divided by B. Again, we'll cross multiply. Let me use pink. So this will be basically the same thing that we were just doing. 11 times the sine of 82 instead, equal to b times the sine of 74. So we're going to divide that over. 11 sine of 82 divided by sine of 74 is our exact value for b, and that is going to be approximated at, this just changes to an 82. Everything else is the same, so it's about 11.33. So 11.33, and again 11.33, and our triangle is solved. I got all three sides in there, all three angles, boom. And again, angle, side, angle case, not a big deal. It's the next case that's going to be a challenge for us because it's what we call an ambiguous case. Okay, so using the law of sines in this what we call ambiguous case. Why is this an ambiguous case? Well, there's many reasons, but first of all, side-side angle is not something that guarantees a triangle. If I gave you two side lengths and then an angle that was not included, so two side lengths and then after those two side lengths some angle, you could be drawing different triangles. Let me try to represent this visually for you. So if I said a side length and I gave you another side length, let me flip this around, angle, side. Okay, I'm trying to make this in my head. If I give you, so there's going to be some side length here that creates an angle. Okay, so let's just say it's a 40-degree angle, and then let's say that this side, so we'd have an angle and then a side and then a side. I just didn't want to write that backwards. So let's say this side length was 10, and then I gave you another side length of 10, and there are lots of ways you could draw that side length of 10. So I could draw the side length of 10, let's say here, with an acute angle, and then your third side, could end up being like this. Or because I don't have to have any particular angle here, it's just another side length of 10, what if I drew my side length of 10 like this? Right? If I drew a side length of 10 here, then I draw an obtuse angle, then my third side could look a lot different, right? It's going to be a lot bigger. So angle side or side angle, it does not guarantee any particular triangle. So what we're going to end up with here is ambiguity, and you're going to see it when we try to use the law of sines exactly the way we did before. So notice right off the bat, we only have one angle, It doesn't mean we can't solve, it just means, or for now, it just means we can't just subtract from 180 to find the other two angles. So I'm still going to start the same way. Let me label this. Let's call this A and B and C, and it really doesn't matter what you're labeling what, but I'm going to go with that. And so we're missing angles B and C, and we're missing side length B here, okay? So what I would do is the same thing I did before. Start with a pair that I know that this 40-degree angle corresponds with this side length of 54. So I can make the sine of 40 over 54 one of my fractions. And then I don't know angle B or side length B, so I would not want to go here and here because that would give me two unknowns in one equation. So I'm not going to go there. But I can go here to try to find angle C because I know the side across from it is 62. So the sine of some angle, which we're calling C, divided by its side length of 62, that ratio should be proportional to the first one, just like before. It's just now, instead of solving for a side length, which is what we were doing in the other triangles, we're solving for an angle. It's okay, we know how to do that. We're still going to cross multiply here. So we're going to have 54 times the sine of C degrees equal to 62 times the sine of 40. I need to divide the 54 over. So the sine of C degrees is going to be 62 times the sine of 40 degrees divided by 54. Okay, now that just looks like a big mess right now. So let me just try to clean that up a little bit. Let's go ahead and approximate that. That's 62 sine of 40 over 54. That's just some decimal. So go away functions. So fraction 62 sine of 40 divided by 54. It's approximately 7.738 thousandths approximately, okay? So all we're saying is the sine of some angle is going to be about that. Obviously that's not a value of an exact value of sine we're going to be able to evaluate using something like the unit circle, right? But we know how to undo sine. We have inverse sine to be able to solve here. So the issue is not that we have the sine of some angle equal to this value. We can use the inverse sine to find the value. The issue is sine is positive in two places. Okay, think about back to our quadrants. Okay, a unit circle, like if we were to put triangles in the unit circle. If I'm calculating the sine of a triangle in quadrant 1, let's say this is my angle C, and I know this isn't a right triangle, but just go with me so you understand, okay? That this opposite side and this hypotenuse is going to give me a positive value, sine is positive here. So if, I don't know if I'm doing a good job of making this make sense, but let me go back to a triangle we know, like a 45, 45, 90, okay? 45 degrees, hit the unit circle at radical 2 over 2 and radical 2 over 2, where this is our cosine, this is our sine. We could make the exact same triangle in quadrant 2. So 45 degrees here, and the coordinates here would be radical 2 over 2, radical 2 over 2. Remember all this, right? Where this is our cosine, this is our sine. Well, cosine's negative in quadrant 2, but sine is positive in quadrant 1 and quadrant 2. So this sine of some angle being equal to 0.738, this is ambiguous. Are they talking about the angle that's in quadrant 1, or are we talking about the angle that's in quadrant 2? So we actually have to do both cases because we don't know which one it is. It's ambiguous, okay? So let's go with, let me draw this out over here again. Okay, we have a triangle in quadrant 1 where we have a positive value for sine. So this is, let's just calculate this first. Okay, I'm going to come back to my picture. If I find the inverse sine, C, it's going to be approximately the inverse sine of 0.738, right? We undo sine with inverse sine. So if I take the inverse sine of 0.738, that's going to give me my angle measurement. So inverse sine, of 0.3738 is going to be about 47 point, let's just say 47.6. So C is about 47.6 degrees, okay? So that would be the angle here. If I put 47.6 degrees, we know 47.6 degrees would be in quadrant 1. So that would be that triangle in quadrant 1. But there's another case, right? Are we talking about the triangle that's in quadrant 1, or are we talking about the triangle that's in quadrant 2? Same exact triangle would have the same exact sign, right? The coordinates here where it would hit the unit circle would be the same. It's just the cosines would change from positive to negative, but the sign's the same in both. So this angle is 47.6 degrees. What I need to know is what is this angle, because that's the other possibility. So the angle from here all the way to here, well, that would be the 180 degrees minus that 47.6. So 180 minus 47.6 is 32.4, 79. Okay, let me just not screw this up. I'm pretty sure I could subtract, but you never know, right? Yeah, 132.4. So there's two possibilities. The sine could be 0.738 at 47 degrees or at 132.4 degrees. So these are both possibilities because we don't know. We aren't guaranteed. Nothing is telling us which one it is. So we actually have to continue to solve for both. Okay, so let's continue here. If C is about 47.6, we'll continue with this path. So if C was 47.6, if we had 47.6 here, then we could subtract 47.6 and 40 from 180. So 180 minus the 40 and the 47.6 means that the remaining angle would have to be 92.4 degrees. So then B would have to be 92.4. So if C is 47.6, B is 92.4. And then we can use a ratio like we did here in order to find the missing side length B. And so let's say the sine of the 40-degree angle over the side length of 54, again, let's use the one that we knew for sure, would have to equal the sine of, now I'm going to go here, sine of 92.4 over that missing side length B. Sine of 92.4 over the missing side length B. So if I cross multiply, then 54 times the sine of 92.4 is going to equal B times the sine of 40. And if I divide 54 sine of 92.4 divided by the sine of 40, I figure out one of my possibilities for B. It's that it's approximately, I don't know, let's ask the calculator, 54 sine of 92.4 over the sine of 40. And that is about 83.94. Okay, so that's one possibility. Now we got to do that again with the other possibility. Okay, and do I have space? We're running out of space. No. Okay, so the other possibility, I did not space this out well, so sorry. Let me section this off. And that looks terrible. That's fine. Whatever, it is what it is. You'll know. Okay, so the other possibility is, or, and actually, since I gave myself all that space, I might as well take advantage, right? Move that up all the way there. Or we could say if C is approximately 132.4, then B would be approximately what? So if, let me get rid of this one now. Okay, so now if this was 132.4, what would be left there? So if we had 180 degrees total, we took out the 132.4, and we took out the 40. All that's left is 7.6 degrees for that angle. So B would have to be 7.6 degrees. I hope I'm putting my degree symbols everywhere. Sometimes I forget those. Okay, so if, now this is all huge because I zoomed out. If C is approximately 132.4 degrees, then B would be approximately 7.6 degrees. And we can write a proportion. We would say, just like before, the sine of 40 over 54 is going to equal, this time, the sine of 7.6 over B. Sine of 7.6 degrees over B. So again, we can go through all the solving, but basically the only difference in what we have here to what we have here is that we're looking at 7.6 degrees instead of 92.4 degrees. So if you wanted to skip a little bit of that work, totally get it, but I don't want to lose anybody here. So I have 54 sine of 7.6 degrees equal to B times the sine of 40 degrees. We divide that over 54 sine of 7.6 divided by the sine of 40, and then that gives us B approximately equal to, again, I just need to change this to a 7.6, and then I get about 11.11. So 11.11. Okay? So those are my possibilities. Possibilities that I get C as 47.6, B as 92.4, and little b as 83.94. Or C is the bigger obtuse angle, and B is really tiny, and then little b is 11.11. So two possibilities. That's a lot of work for that ambiguous case. The preferred option with the side-side angle is that it doesn't work at all. So it's either a straightforward case, okay, if you have if you have angle, angle, side, if you know two of your angles, there's no ambiguity in what the third angle has to be, that's going to be a straightforward case. If you have angle, side, angle, then the side is between the two angles, but again, you've got two angles, there's no ambiguity in what that third angle is going to be. It's when you have side, side, angle that is going to be ambiguous, and so it's possible that there are two separate triangles that are created, or it's possible that you don't end up with a triangle at all. And how are you going to know? So let me show you. This is clearly one that doesn't work. It says show that there's no triangle for which a equals 60, little a is 4, and b is 14. I'm going to show you how you know right now. First, let's try to sketch this out. I think it's useful to do that. So let's call this A and B and C. And my draw tool is on, so that looks funny. Okay, so it's saying A is 60 degrees, and little a is 4, and little b is 14. So again, this is a angle side side or side side angle case. There would be ambiguity going on with the fact that we're missing two angles. So let's say we start this the same, because I know that this one isn't going to work, and I'm telling you here, show that there is no triangle for which this works, but how are you going to know? Well, we would start the same way, okay? If it's not saying show it, it's just saying solve it, how are you going to know this is a no solution problem? Well, if we set up our proportion of this sine of 60 degrees over 4 equal to let's go with, again, I don't want to use, change colors. I don't want to use C and little c because I don't know either of those. So I would maybe use B here with B here because I know one of those. So I would say the sine of B over 14. All right, when I go to cross multiply and solve this, I have 4 times the sine of B equal to 14 times the sine of 60. And I divide by 4, so the sine of B is going to equal, I should be putting degrees in all these, I'm sorry, 14 sine of 60 degrees all divided by 4, and that is something that we can approximate. So let's do that. 14. This is where we're going to know that we have an issue. Well, that we have to recognize that we have an issue. Come on, calculator. All right, so 14 times the sine of 60 degrees divided by 4 ends up being 3.03. 3 approximately 3.03. And this is when I know this is not going to work, okay? So up here, I didn't say anything because we already had an overload of information going on. Sine is positive in 2 quadrants. That's still true here, but sine also has a max and a min, which is why it's really important to understand what our basic sine, and cosine later functions are going to look like. Sine has a max and min. Remember our sine curve? Clear all this out. Y equals the sine of x. With the highest that it goes is 1, and the lowest that it goes is -1. So when we take the sine of an angle, it has to be a value between -1 and 1. And since this is not a value between -1 and 1, I know there will not be an angle for which the sine is 3.03. Right? Sine, let me make this plain English. The sine of, oh my, can't write. One more time. I actually have red spilling over everywhere, so how about this blue? The sine of an angle must be between -1 and 1 inclusive. Like I can get to a minimum of -1 and a max of +1, but because 3 is beyond that, this is no good. So this tells me that there is no solution here. We wouldn't call this the ambiguous case. It is quite clear that's not going to work. Okay, so this is the case without a solution. So you want to make sure that you're approximating at this point up here. Approximate what you're trying to take the sine of, because if you get a value between -1 and 1, then you can proceed and solve for the 2 possibilities, the 2 possible triangles that will work. And if you get a value here that you're trying to take the sine of that is less than -1 or greater than +1, if it's out of the range for sine, then there's not going to be a solution. Okay? So hopefully that makes sense. I know this is a lot to take in, but do your best with it and give the practice a shot. And as always, if you need some extra help, then reach out. Until next time, take care.